In this lesson, we're going to solve minimum connector problems using two different algorithms, Prim's algorithm and Koskals algorithm. So here's some terminology for this topic. We've already come across a tree. A tree is a graph with no cycles. A spanning tree is a tree that connects all of the nodes in a network. So this is an example of a spanning tree for this network. As you can see, every node is connected to that tree. Consider the relationship between the number of arcs and the number of nodes that you would need in a spanning tree. So you can see for this one we've got 5 nodes and that takes 4 arcs to join them. And in general, for any spanning tree, the number of arcs is always the number of nodes minus 1. A minimum spanning tree for a network is a spanning tree that has the smallest total weight. By inspection, look at this network and draw a minimum spanning tree. You can see the minimum spanning tree there uses those 4 arcs, and they are the 4 arcs of the smallest weight that will give us a spanning tree. So the first algorithm we're going to use is called Prim's algorithm. This will find us a minimum spanning tree. Prim's algorithm always starts from a particular vertex, and in this case we're going to start from vertex A. It's important when you're performing an algorithm that you write down each of the steps clearly. So for this network here, the first step in Prim's algorithm is to pick the smallest arc that connects to the vertex that we are starting with. So in this case we're going to start at vertex A and choose the smallest arc coming from A. So that is arc AC with a weight of 3. I'm going to put the order of the arcs into a table. So arc AC was added first and its weight was 3. The second step in Prim's algorithm is to consider all of the arcs that connect to the graph that we have already started to draw. So we need to consider the smallest arc coming from either vertex A or vertex C. So the smallest arc coming from here is AD with a length of 4. So we add that to the table, arc AD, weight 4. We then continue in this manner, always adding a new vertex, add a new arc to the connected graph that we've started to form. And we continue with this until we have got a spanning tree, so until we've included all of the vertices, all of the nodes. So the next arc we are going to add is DF, which has a weight of 2. Now the next arc, we can't add CF, which is 5, because that wouldn't be adding a new vertex to the tree, and indeed it wouldn't be a tree if we added CF, because we would be creating a cycle. So we need to consider just the vertices that have not yet been added to the tree. Now there are actually 2 possibilities here, because BD and FE have both got a weight of 6. We can choose either of these, as long as you list which one you've used. So if we choose BD, add that to the table. And the next one we're going to add is FE with a weight of 6. So we've now finished. We know we've finished because we have added all of the vertices, so we've created a spanning tree. We now add together the weights, and that gives us the weight of our minimum spanning tree, which is 21. So another name for this problem is a minimum connector problem, because we're trying to find the minimum weight to connect all of the vertices to each other. So this could be used in networking, for example, where a number of computers, for example, may need connecting to a network. Can also be used in scenarios like roads. So if we were looking for a road network that connected various different towns, a minimum connector might be appropriate there. The second algorithm we're going to use serves the same purpose, but it has slightly different instructions. This one is called Koskals algorithm. So in Koskals algorithm, we don't start from a particular vertex. The first step for Koskals algorithm is to choose the smallest arc in the entire network. So looking at the network, we can see the smallest arc is D to F. And again, we're going to put these into a table. So arc DF has a weight of 2. We then consider the rest of the arcs that are yet to be added, and we're going to choose the smallest arc in the network that does not form a cycle with the arcs we have already picked. So the second arc we're going to choose is A to C. Notice that it's not connected to DF, it doesn't need to be in Koskals algorithm, and it doesn't form a cycle, so that is the next one we can choose. So A to C has a weight of 3. Continue in this manner until again you have a spanning tree. So A to D with a weight of 4 is added next. Now the next smallest would be C to F, which has got a weight of 5, but that would form a cycle. So we move on and choose the one after that. We can choose either of the two arcs of length 6. Let's choose BD with a weight of 6, and then we'll choose EF with a weight of 6 again. And we've now found a minimum spanning tree, so we can add up the weights. Now Prim's and Koskals algorithm will both give the minimum spanning tree, so they will both give the same total. However, the two algorithms may give two different spanning trees if there is more than one minimum connector for that particular network. Pause the slide now, and for each of the 3 networks, first use Prim's algorithm starting from vertex A each time, and then use Koskals algorithm to find the minimum spanning tree for each of the networks. So the first network. So the first graph, starting with Prim's algorithm from vertex A, the first arc to be added is arc AE with a weight of 26. We're then going to keep adding arcs to the connected graph that we have started to form. So the next arc to be added is AD 28, then CD 25, then BC 12, and finally CF 26. So that gives us a total weight of the minimum connector of 117. So then Koskals algorithm for the same network. So this time we're just going to choose the smallest arc on the entire network, which is BC with a weight of 12. I'm going to continue adding arcs of the lowest weight, ensuring that we don't create a cycle. So the next arc is CD 25. We then add AE 26, then CF again 26, and finally AD 28. So that also gives us a total of 117. So then for the second graph, we've got Prim's algorithm giving us first from AD, and following that gives us each of these arcs and weights in turn. So a total of 80. Let's just compare that to Koskals algorithm. So Koskals begins with BE, and continues like this. So the total again is 80. Remember that you will always get the same total regardless of which of the algorithms you use. However, the order will be different, and sometimes the tree that you get will be different as well if there is more than one tree. So finally, Prim's algorithm from A for the third graph gives us the following solution. With a total of 72. And Koskals algorithm for the same network also gives us a weight of 72. One of the main benefits of Prim's algorithm over Koskals is that Prim's algorithm can also be modified to work if the network has been given as an adjacency matrix. This is more difficult to do with Koskals algorithm because one of the steps in Koskals involves checking for cycles, and this is difficult to do in an adjacency matrix. So Prim's algorithm, in order to carry it out from an adjacency matrix, the first step is to put the network into an adjacency matrix. So if there's a direct arc between two nodes, then the weight is shown as an element in that table. If there is no direct edge, then a dash is input instead. So filling in each element of the adjacency matrix. See that B to F, there is no direct edge between those two, so there's a dash there. Also remember that if the network doesn't have any directed edges, then it will be symmetrical about the leading diagonal. Okay, so once we have got the network represented as an adjacency matrix, we can start Prim's algorithm. This is Prim's algorithm in matrix form. The first step is to start at the named vertex. We're going to start at A, and you circle A in this case, so circle the first vertex. When a vertex has been circled along the top, that shows that it has now been added to the spanning tree. The next step is to cross out the row corresponding to that vertex. The reason it's being crossed out is because it now does not need adding anymore. It's already been added to the tree. We're still going to fill in a table showing the order of the arcs as they are added. So we are now going to consider the circled nodes. In this case, there's only one in the first step, just node A. We're going to look down that column and choose the arc of smallest weight and circle that. So AC is the smallest arc from A. Now that we have chosen AC, we can now circle C along the top to show that node C has now been added to the tree, and we can cross out row C because it now does not need adding again. Don't forget to put AC weight 12 into the table. We're now going to consider both columns A and C because the next arc could come from either of those two vertices. We're going to repeat step 2 until we have circled all of the nodes at the top. So looking down columns A and C, we can see that CD is the next lowest weight. So D is added to the circled nodes at the top. Row D is crossed out from the table. And CD, weight 13, is added to the table of values. I'm now going to look down all three of the circled columns. Select 14 as the smallest weight. This adds vertex B. So we're going to circle vertex B, cross out row B, and add BD 14 to our table. The next arc that needs to be added has a weight 16, it's CF. So we're going to add node F to the top, cross out row F, and add CF to our table. Then finally, we've got EF of weight 11, add E to the circled nodes, cross off row E, and we've completed our table with EF. So this gives us a total spanning tree of 66. For each of these two adjacency matrices, use Prim's algorithm to find a minimum spanning tree starting from A each time. So this time, as we do the algorithm, we're also going to draw the tree as we go along. So we're going to start with node A. I'm going to cross off node A from the rows. I'm going to select the arc of minimum weight, which is AB 21. I'm going to draw that as part of the graph. So A to B with a weight of 21. We're going to also add AB and its weight to the table showing the order that the edges were added. So adding B to the list of circled nodes at the top and crossing off row B. Next arc that we're going to select is going to be BD 24. Again, we're going to add that to our tree and also to the table. Circle D and cross out the row. The third arc to be added is DE14. We're going to add that to our tree and to the table. Circle E and cross off row E. Next, we're going to add CD. Add CD to our tree and to the table. Circle C, cross off row C. And then finally, C to F 16 is added, and that completes the algorithm. So the minimum spanning tree we have found has got a total weight of 94. So for the second network, we're going to start again with node A, circle it at the top and cross off the row. We're then going to look down column A for the smallest weight, which is 4. So that corresponds to arc AC. I'm going to draw that on the diagram and also add it to the table. I'm going to add node C by circling it at the top and crossing off the row. Now I'm going to look down column A and column C for the smallest weight. That is going to be CF with a weight of 4. So add CF to the diagram and to the table. Then going to add F by circling it at the top and crossing off the row. Now looking down all three columns, we can see that CD is the next smallest. So adding CD to both the table and the graph. We're then going to circle node D and cross off the row. The next smallest weight is then AB with weight of 5. Add that to the table and the graph and add node B. And then finally, we're going to add BE with a weight of 6. And that completes the algorithm. So that gives us a minimum spanning tree with a total weight of 24. Now complete exercise 2.1 on page 26.